Hello everyone, this is Hao Wan, and today I'm presenting our work Context Uncertainty in Contextual Bandits with Applications to Recommender System. So this is joint work with Yifei, Haoding, and Bernie. Essentially, the problem of recommender systems is that we're given a lot of preferences from the users to the items, for example, movies. And given these observed preferences, we would like to predict the unobserved ones. And modern recommender systems rely heavily on the usage of latent representations. For example, one can usually learn the latent representations by matrix factorization. We can factorize a large rating matrix on the left R here into two smaller low-rank matrices P and Q. And specifically, each row in the matrix Q will be the latent representation P for an user, and each column of the matrix Q here would be the latent representation Q for an item. So ultimately, the model will predict the rating from a user to an item using the inner product of P and Q. And another example would be to learn deep latent representation via collaborative deep learning. Essentially, collaborative deep learning will try to learn deep latent representation X for an item from autoencoded, or more specifically, probabilistic autoencoders. And additionally, the model will also learn the latent representation U for each user and the latent offset epsilon for an item. And finally, the model will try to predict the rating from a user to an item using the inner product of U and X plus epsilon. The third example, which is more relevant to our talk here, would be to learn the deep latent representation via recurrent neural networks, or RNN. So essentially, we will have an RNN to learn the deep latent representation H for a user at time t plus 1. And of course, the RNN will additionally learn the latent representation X for each item. And finally, it's going to predict the rating from a user to an item using the inner product of H and X. So basically, this performance of modern recommender systems, it relies heavily on the quality of representations in the latent space. However, these performance often saturated if the system is deployed in an interactive setting after multiple time steps. For example, the system at first may find the users that likes action movies a lot, and the system will just try to keep recommending her action movies, and the reward, or we can say accuracy, increases over time, at least at the beginning. And then the reward kind of saturated because the system failed to explore more of the customers or the user's interests, right? But ideally, what we want is something like this. We want the system to find that the user likes action movies and recommend to the user action movies, and at the same time, explore other movies. So at the beginning, the reward will still increases, but as time goes by, we hope that the reward will keep increasing thanks to the exploration done by the system. So we can see that the recommendation obviously rely on the learned latent representations, and this good latent representation obviously rely also heavily on effective exploration. Unfortunately, this is actually causing a chicken and egg problem because the effective exploration actually also relies on good latent representations, because the exploration always needs to happen in the latent space as well, because we have everything is based on the latent representations. So how do we approach this problem and get us out of this chicken and egg problem? And our solution would be to consider the context uncertainty or latent representation uncertainty in recommender system. In that way, we can address the problem of effective exploration and good latent representations at one time. So basically, when computing the score for item K for user at time t, we are going to compute the sum of two terms. The first term would be the relevance term, and the second term would be the diversity term. So next, I'm going to talk about these two terms in detail one by one. For the relevance term, we can see that this xk is actually the latent representation for item k. So this representation can come from any neural networks, obviously. And this theta k is the latent representation for this user at time t. And this latent representation too can come from any neural networks. And this neural network has to take as input the previous t-1 purchase items by this user and produce the final representation for this user. So we can see that this inner product of xk and theta t would represent the relevance between the user at time t and the item k. Next, let's go to the diversity term. So here we have this capital XT, which is actually a collection of the latent representations for all of the t-1 items this user purchased before time t. So we can see that this is actually a matrix because it has t-1 vectors. And what is xt transpose times xt? This large matrix actually measures what has been explored, right? And this is the latent space this user has explored until time t. And adding this identity matrix ID is just to prevent singularity. You can think of it as a regularization term in the system. And taking the inverse of this whole matrix, basically this will try to measure what has not been explored by the user. So this is the latent space this user has not explored until time t. And then this final large term would represent the diversity score for item k. So basically it says how item k is different from this user's previous items. So the larger this term is, the more different item k is from this user's previous items. So we can see that this exploration can be based on the diversity in the latent space. But is it sufficient? Let's consider an example where the latent representation happens to be the same for all the items. So basically, for each item, the latent representation xk would be all identical or equal to x star. And if this is the case, then all the items would have identical diversity scores, right? According to the diversity term here, then we can see that this is actually not good enough. For example, item 1 may have a representation x1 that happens to be just initialized as x star, but actually the model is not very certain about the fact that x1 is equal to x star. Based on this intuition, ideally we would like this system to focus the exploration more on this item 1 as opposed to the other items, right? And to capture this kind of uncertainty, we then need to consider both the mean and variance of the item representation xk. So basically, the original deterministic sk would become a random variable with mean mu k and variance sigma k squared. And correspondingly, capital XT, which represents the collection of all the latent representations until time t-1, or we're going to denote it as capital DT here. So basically, we're going to have a third term included when we are computing the final score for item k. So this is what we call the uncertainty term. So what's the uncertainty term? So basically, this uncertainty term is the infinity norm of sigma k. So this basically represents the uncertainty score for item k and measures how uncertain we are about item k's representation. Ideally, at the beginning, item case representation will have high uncertainty. That means we're going to have a very large uncertainty term here. So this infinity norm of sigma k will be relatively large. And as the time goes by, the system will tend to recommend item k more frequently because the system feels that he is more uncertain about item k's representation. But as the system collects more and more data, it will be more and more certain about item k's representation. Therefore, correspondingly, this infinity norm of sigma k will get smaller and smaller. And gradually, we're going to focus the exploration on the other items which has higher uncertainty. So this is exactly what we want, and this is the intuition of the overall method that we propose. And as we mentioned before, our method actually is compatible with any base models. We can see that this theta t, the representation for the user at time t, it actually can come from any base model. So it can be a recurrent neural networks or RNN of different variants. For example, we can use a GRU or TCN or HRNN to take as input the previous purchase t-1 items by the user and to finally output the final representation for this user at time t. Or we can equivalently using a transformer to compute this theta t, or we can use matrix factorization as well. So to showcase that our model can be compatible with any base models, this is a quick experiment result. We can see that this is the accuracy of the reward for different base models, GRU for RAG, TCN, and HRNN. And this is the result when our model is combined with the base models, GRU for RAG, TCN, and HRM. We can see that our model can actually work with all of them and improve the long-term reward for all the base models. In terms of theoretical analysis, we also prove that for a user at time t, the difference between our method, REN's estimated reward, and the true reward for item k is actually bounded by a weighted sum of the diversity term and the uncertainty term. So these two terms are basically they are the second term and the third term that we proposed in the previous slides. And we can also prove that after t time steps, the difference between the optimal cumulative reward and REN's achieved cumulative reward. So this is the regret that we have been talking about in contextual bandits. So the difference between this reward has a sublinear bound. Basically, this says that we actually have a rate optimal sublinear bound on the regret, and it's equivalent to saying that the average regret, which is regret over t, this will converges to 0 as t approaches infinity. And note that our method actually focuses on context uncertainty, which is actually very different from typical contextual bandit that focus on reward uncertainty here. So typically in contextual bandit, there will be uncertainty, but the uncertainty is only in the reward. So basically, the uncertainty is irrelevant or independent of each item, xk here. And the representation or the context xt is actually deterministic. And this is particularly problematic if xt is in the latent space, as we mentioned before. So to handle this problem, we propose to focus also on the context uncertainty as well in our proposed REM method. So in this case, we're going to have a probabilistic context. And as an example, you can assume that this xk is actually a Gaussian random variable with a mean mu k and variance sigma k square. And this sigma k square actually represents the context uncertainty in contextual bandit. Of course, we still have this reward uncertainty considered in the model. And let's first see how our model performs in the toy dataset. Here we have 3 toy datasets with 28 unique items. So these are items with different ground truths, 8-dimensional latent representations, HK. So we have 3 toy datasets with different sizes. We have SYN-S, which has 15 users and 28 items. So for this SYN-S, this small data set, all the 28 items, they are unique items, they're different from each other. And we have SYN-M dataset, which also has 15 users, but it has much more items. It has 280 items. So this is actually a repeated version of the SYN-S dataset. And we have the SYN-L dataset, which has also 15 users and has 2,800 items. The reason that we have repeated version of these unique items is to evaluate our methods effective exploration in the latent space. Because when the item space is large, it's actually very inefficient to explore in the item space. So instead, it will be much more efficient to explore in the latent space, which is actually also one of the advantage of our methods. And for the simulated experiment, basically it's quite standard. At each time step, we're going to randomly choose one user, and we're going to ask the model to recommend 4 items and return the reward to the model. And the model, of course, it's going to collect the feedbacks and fine-tune the model. So this is the baseline. As we mentioned before, our method can take any model as base models. But in this paper, we focus on sequential base models. But here we use 3 state-of-the-art RNN-based models. We have GRU for RAC, which is gated recurrent units for session-based recommendation. We also have TCN, which is temporal convolutional networks for sequential recommendation. And we also have another state-of-the-art method, HYNN, which stands for hierarchical recurrent neural networks for sequential recommendation. So this is the result for the small toy data set. We can see that this is the reward over time or accuracy over time for different base models. The horizontal axis is the time steps, and the vertical axis shows the accuracy, and more specifically the reward or the precision, anything that measures how accurate the recommender system is. So we can see that this base model, the accuracy will increase at the beginning, but gradually it's going to saturate. And this is the performance for our methods using these 3 base models. We can see that our method can actually perform effective exploration using these base models and push the performance or the long-term reward closer to the oracle, right? And more specifically, if you take a closer look at the base model, you can see that the best base model is actually HYNN, which is also this is actually the most recent base model that we use. And our method using HYNN as base models can also achieve the best performance among all the REN variants. And we can observe similar improvements in the other 2 toy data sets. And here are the ablation study on the diversity term and the uncertainty term. So this is the performance for our method without the diversity term on the large toy data set. And this is the performance on the same large data set, but with the diversity term. You can see that when the item space is very large, this diversity term can actually help effective exploration in the compact latent space, right? And it actually helps a lot. And for the uncertainty term, you can see that this is the performance of our method without the uncertainty term. And this is the performance of our methods with the uncertainty term. And similarly, on the other toy data set, SYN-Small, this is the performance for our method without the uncertainty term, and this is with the uncertainty term. So basically, you can see that this uncertainty term can actually help explore uncertainty items and pushes the long-term reward closer to the optimal or the oracle. And we'll also evaluate our methods on real-world datasets. We use 3 recommender system datasets, movie length 1 million, which consists of about 6,000 users and 3,000 items and 1 million interactions. And we also use a subset of the Netflix dataset, which has about 480,000 users and 17K items and over 100 million interactions. Lastly, we have the Trivago dataset, which has about 700,000 users and 900,000 items and 900,000 interactions. So this is the result for the movie lens dataset. We can see that this is the performance for the base models. The accuracy increase at the start, but gradually tend to saturate at some point, and this is the result for our methods using all these base models. And we can also see that SYN-N, which is the orange line here, it actually has the best performance as base models. And our method, RENH, which is SYN-N with our method REN, can perform the best among all the methods. So this is the result for Netflix. Now we can see that our method can also improve upon the base models, SYN-N. So basically it says that our REN performs effective exploration to achieve higher long-term reward. And for the last recommender system dataset, it actually has a slightly different setting because it has impression data. So what's the difference exactly? If you look at the previous 2 datasets, movie lens 1 million and Netflix, you can kind of imagine that at each time stamp, the models will recommend items from the entire item set. So this is like 3,000 items and 17K items respectively. But for Trivago dataset, at each time t, the models will recommend items from a candidate set of 25 items. So this is only the 25 items that has been shown to the users. And this is called impression data because we know exactly what items are shown to the user. So we do not use the entire set of 900K items as the candidate set, and instead we only use the small set that has been shown to the users. And this is a result. You can see that this is the performance for the base models, and this is the performance for our REN using these base models. We can see that our REN can perform effective exploration to prevent accuracy drop and maintain high accuracy. So to conclude, we here identify a chicken and egg problem when exploring in the latent space, and we propose a framework of context uncertainty and instantiated with REN to handle this problem. And we also provide theoretical guarantees that our REN can achieve the rate optimal regret bound. And experiments show that we can achieve state-of-the-art performance on both synthetic and real-world recommender system datasets. More details on these papers and in terms of experiments and theories can all be found at the link of the paper here. Thank you.